then will be used in 3 use cases: scientific data management, life sciences, and big data. And I'll just talk briefly about the use case to motivate that more and then go into the details. So a use case that's actually very prominent and very interesting also because we have a research institute just next to Berlin that's focusing on that, is climate data analysis. So there is the Potsdam Institute of Climate Research, which is advising the World Climate Council of the United Nations with respect to climate change. They are a research institute that basically creates and analyzes climate models and tries to predict the effect of global warming and other things in the future. And the interesting thing about this use case is that it's on the one hand, it's a wonderful data generator that is a very practical application. It's like TPC-H, but with a real environment, namely complex climate simulation data.
On steroids, I'd say.
Yes. And they have, just to give an example, so the data looks like they have parameters like surface pressure, air temperature, various temperatures, wind speeds, humidity levels, cloud covers, and so on. A total of like 200, if you were talking about the Yahoo's measures. And they are putting a grid over the world, just to give you an idea of the massive scale. If you put a map, just a grid over Germany in a 2-kilometer resolution, you would get 10 terabytes of data for a simulation that's 3 months. But of course, they're actually not simulating just Germany, but the entire world, and of course not only 3 months, but actually years and decades. So we see that they're really talking about petabytes of data that are being managed here. So they're currently using a big cluster of thousands of computers to generate climate models. The problem there is, though, currently they don't have a really good way of analyzing them, particularly if it goes beyond a single climate model. So interesting tasks that currently cannot be carried out and that we aim at carrying out with this massive parallel architecture I'll talk about is, on the one hand, to validate climate models. That means you take a climate model and you compare it to the past and see how well does it fit the past. So basically joining real data from climate measurements around the world with the prediction of a model. And then you want to find hotspots in the climate models, like where's the monsoon, what about drought, what about flooding. A very interesting example in that context, by the way, particularly for people from Asia, is that many climate models predict that the monsoon in Asia will cease to come in about a decade or 2 if the climate models are correct with current assumptions and parameters. So that means there will be no monsoon anymore, which will of course have heavy impact on the agriculture, the economies in that region. And so they are actually currently advising the Chinese government and others on how to adjust to this possibility. But at the same time, there's lots of different climate models with different probabilities of things happening, right, with different assumptions. So that means now what they would like to do is to aggregate climate models and compare climate models and find how long does the monsoon vanish, because what they also found out in several simulations, the monsoon comes back again after another decade, which is kind of interesting. So basically compare climate models, analyze them, and in this way identify interesting hotspots. So the necessary operations, there are on the one hand operations that we are very familiar with as database people, like filtering, aggregation over sliding windows and joins, but then also a little bit more complex operations like multidimensional sliding window operations across the time and the space, and geospatial temporal joins associated with the uncertainty that comes from the fact that a certain climate model has a certain probability of occurrence. So those are the kind of operations that this use case looks at. We're also looking at 2 other use cases in that context. So one of them is text mining in the biosciences, where we basically use the PubMed database, and there's a colleague in Humboldt University Berlin who's working in that field, basically in the field of information extraction and information management for the life sciences. And he's doing text mining, and he's very interested in how to employ such a massively scale-up architecture in order to analyze and provide structure to this large body of work in the biosciences. And another interesting aspect of work is cleansing of linked open data, where another colleague, Felix Naumann from the Hasso-Plattner Institute in Potsdam, is interested in applying the technology for data cleansing and basically ETL-ish operations, but on linked open data, which is actually very dirty data. How do you integrate that? How do you merge and combine it? So those are use cases which go, if you can see that, beyond traditional SQL operations to some extent. With that motivation, let me now describe initially the architecture of the system that we have begun to build in the last year. Particular focus on what we call the packed programming model, which is a programming model which follows this paradigm of MapReduce of second-order functions for parallelization that extends it. And then I'll talk about the network execution engine, which is really our runtime system. And then talk a little bit about how we parallelize packed programs, the current work, but also give you an outlook on the future work, because this is very much work in progress. We've embarked on this effort a year ago. We have an initial prototype. We have a lot of backtip and mailing wire operational right now, but the next years will be hardening that prototype and building upon it.
So, Volker, yes? You said that in the examples that you gave, that they were sort of not well suited for the SQL world. Is that a question of expressiveness, or is it a question of efficiency, or both?
Well, for me, SQL is more expressiveness. So I always try to differentiate the efficiency argument, which is really the runtime engine, from the expressiveness part. So that's also, and we can talk about it maybe later on in the discussion. For me, the popularity of the MapReduce model to a large extent is also because people, and that's the feeling that I get from attending Hadoop user group meetings, people like to think that way and express their programs more in this way than in declarative SQL. That's to some extent what this NoSQL movement, the way I see it, has become about, at least from the Berlin user group perspective. That said, you could, of course, write those things in SQL. It just would be looking a little bit more complicated and sometimes with this MapReduce paradigm. So that's one aspect. The other aspect is, of course, this massively parallel scale-out is also a challenge, clearly. And I'll talk about that as well. But that's then when I talk about this network execution engine part. So I try to differentiate because nothing prevents you. And I actually talked with some people of you this morning about that already. Nothing prevents, in my opinion, you just to add MapReduce on top of DB2. I mean, map is just a function call. You can use your filter, make and pipe operations to create it, right? And reduce is just your aggregation, right? So in this way, it's very easy to offer that interface. And that actually would probably already open some of those applications for MapReduce. The only problem is you have to start optimizing user-defined functions, and there will be some issues coming up, but that's really the challenge here, right?